Welcome to our fascinating journey into quantum statistics. Today, we'll explore a remarkable branch of physics that helps us understand the behavior of particles at the tiniest scales of our universe. Let's dive into the core of quantum statistics. In the classical world, we use probability distributions like Maxwell-Boltzmann to describe particle behavior. But when we zoom into the microscopic world, everything changes. Quantum mechanics introduces two revolutionary concepts: the indistinguishability of particles and the quantization of energy levels. Imagine particles so small that they lose their individual identities, and energy that comes in discrete packets rather than a continuous stream. This is where quantum statistics becomes our guiding light, helping us understand complex phenomena like superfluidity, superconductivity, and the behavior of gases at extremely low temperatures. Why do we need quantum statistics? Quantum statistics emerges as a critical scientific approach when classical physics reaches its limits. In the microscopic world, particles behave fundamentally differently from our macroscopic understanding. Unlike classical physics, where particles are distinct and energy flows continuously, quantum statistics reveals a world where particles become indistinguishable and energy moves in discrete, quantized steps. Imagine particles losing their individual identities, becoming more like identical quantum waves than distinct objects. Their energy doesn't smoothly change, but jumps between specific levels, like steps on a staircase rather than a gentle ramp. This radical perspective requires entirely new mathematical frameworks to understand and predict particle behavior at atomic and subatomic scales. Quantum statistics provides this crucial bridge, offering a mathematical language that can describe phenomena classical physics cannot explain. It transforms our understanding from tracking individual particles to understanding their collective, probabilistic behavior in the quantum realm. Let's explore the Maxwell-Boltzmann distribution, the cornerstone of classical statistical mechanics. Imagine a classical gas where each particle is unique and can have any energy level. This distribution describes how particles are spread across different energy states in such a system. The key characteristics are fascinating. Particles are distinguishable, energy levels are continuous, and they follow classical motion laws. The mathematical formula we see here represents the probability of finding particles at a specific energy level. Notice how the distribution depends on temperature. As temperature increases, particles can access more energy states, creating a wider spread of possible energies. The Maxwell-Boltzmann distribution provides a classical statistical description of the distribution of particle energies in a system. While effective for classical systems, it fails to capture the quantum nature of particles at low temperatures or in microscopic systems. This limitation prevents it from accurately explaining phenomena like superfluidity or the behavior of degenerate gases, emphasizing the necessity of quantum statistics for a comprehensive understanding of these systems. Enter the Bose-Einstein distribution, a quantum statistical marvel. This distribution describes bosons, particles with integer spin that can occupy the same quantum state. Unlike classical particles, bosons can pile up in identical states, creating extraordinary phenomena. The most mind-blowing manifestation is Bose-Einstein condensation, where at extremely low temperatures, a large fraction of bosons collapse into the lowest energy state. Imagine a crowd of particles suddenly deciding to huddle together in perfect synchronization. Helium-4 is a perfect real-world example, demonstrating this incredible quantum behavior. Let's delve deeper into Bose-Einstein statistics. The fundamental principle here is particle indistinguishability. Bosons become virtually identical entities. At sufficiently low temperatures, something magical happens. Bose-Einstein condensation occurs. Picture a group of particles so cold that they collectively occupy the lowest energy state, behaving almost like a single, giant quantum object. This leads to macroscopic quantum phenomena like superfluidity, where liquid helium can flow without any friction. It's as if the particles lose their individual identities and start moving as a unified, frictionless entity. Welcome to the fascinating world of Fermi-Dirac statistics. Unlike bosons, fermions follow a completely different set of rules. These particles, including electrons, protons, and neutrons, obey the Pauli exclusion principle, which is like a strict quantum mechanical law. Imagine a classroom where no two students can sit in exactly the same seat. That's how fermions behave in quantum states. This unique characteristic leads to some of the most intriguing phenomena in physics, including the degeneracy pressure that stabilizes extraordinary cosmic objects like white dwarf and neutron stars. Let's unpack the remarkable features of Fermi-Dirac statistics. The cornerstone principle is the Pauli exclusion principle. No two fermions can occupy the same quantum state simultaneously. This might sound simple, but its implications are profound. At absolute zero temperature, fermions fill available quantum states up to a specific energy level called the Fermi energy. Think of it like filling a multi-story building. Each floor gets occupied systematically, with no two individuals sharing the exact same room. This principle creates what physicists call degeneracy pressure, a quantum mechanical force that prevents complete gravitational collapse in stellar remnants. This slide highlights three key statistical distributions in physics: Maxwell-Boltzmann, Bose-Einstein, and Fermi-Dirac. Maxwell-Boltzmann statistics describe classical particles. Bose-Einstein applies to bosons, which can share the same state, and Fermi-Dirac applies to fermions, which cannot share the same state. At high temperatures, all distributions behave classically, while at low temperatures, unique quantum effects like Bose-Einstein condensation for bosons and Fermi gas degeneracy for fermions become significant. Now, let's compare fermions and bosons, two fundamental types of quantum particles with dramatically different behaviors. Fermions, which include electrons, protons, and neutrons, have half-integer spins. They're the rule followers of the quantum world, strictly adhering to the Pauli exclusion principle. In contrast, bosons like photons and helium for atoms have integer spins and are the free spirits of quantum mechanics. They can happily occupy the same quantum state, leading to fascinating phenomena like Bose-Einstein condensation and laser action. Their different behaviors arise from their intrinsic quantum mechanical properties. Quantum statistics isn't just an abstract theoretical concept. It's a powerful tool for understanding real-world phenomena. From explaining the behavior of ideal gases to unraveling the mysteries of radiation and condensed matter, quantum statistics provides insights into systems where classical physics falls short. Imagine being able to predict how particles behave at the tiniest scales, where traditional laws of physics break down. We'll explore how quantum statistics helps us understand everything from the radiation emitted by stars to the conductivity of metals. Let's dive into the world of ideal gases through the lens of quantum statistics. An ideal gas is like a tiny universe of particles in constant, random motion. While classical mechanics provides one perspective, quantum statistics reveals a deeper understanding. At very low temperatures or for small particles, quantum effects become crucial. The distribution of molecular speeds and energies changes dramatically when we apply quantum statistical principles. It's like zooming in on a swarm of microscopic dancers. each moving according to quantum mechanical rules. The Maxwell-Boltzmann distribution describes the spread of velocities among particles in a classical gas. It predicts that most particles have speeds around a certain average, with fewer particles moving much slower or much faster. The distribution is influenced by factors like particle mass, temperature, and the Boltzmann constant. Understanding this distribution helps in predicting the behavior of gas particles in various conditions, providing insights into properties such as pressure and temperature. This slide explains how the energy of an ideal gas particle relates to its velocity, using the equation equals half mv squared. It introduces the Maxwell-Boltzmann distribution, which describes the probability distribution of particles' kinetic energies. The probability of finding a particle with a specific energy is higher for energies close to the thermal average and decreases rapidly for higher energies. At high temperatures, classical statistics accurately predict particle behavior. However, at low temperatures, classical approaches fail and quantum statistics become necessary. Now we enter the quantum realm of gas behavior. At very low temperatures or high particle densities, the classical Maxwell-Boltzmann distribution isn't suitable due to significant quantum effects. Instead, Bose-Einstein distribution is used for bosons like photons and helium for atoms, where particles tend to accumulate in the lowest energy state at very low temperatures, known as Bose-Einstein condensation. Fermi-Dirac distribution applies to fermions like electrons and neutrons. At absolute zero, fermions fill available quantum states up to the Fermi energy due to the Pauli exclusion principle, which prevents more than one fermion from occupying the same state. The Fermi-Dirac distribution formula predicts the average number of fermions in a state with a specific energy, considering the effects of temperature and chemical potential. This distribution becomes significant at low temperatures when classical mechanics no longer adequately describe particle behavior. Prepare to be amazed by the black-body spectrum, a crucial application of quantum statistics that revolutionized our understanding of radiation. A black body is an ideal object that absorbs all incoming radiation and emits radiation based solely on its temperature. Classical physics utterly failed to explain the observed radiation spectrum, predicting an impossible infinite energy at high frequencies, a problem known as the ultraviolet catastrophe. Quantum mechanics, specifically Planck's law and Bose-Einstein statistics, provided the breakthrough solution. Let's explore a pivotal moment in physics history. Before quantum mechanics, classical physics made a catastrophic prediction about radiation. The Rayleigh-Jeans law suggested that as frequency increases, radiation intensity would approach infinity, completely contradicting experimental observations. This ultraviolet catastrophe was a major crisis in physics, exposing the fundamental limitations of classical theory. It was like trying to describe an ocean's complexity using only a child's paddling pool. The classical model simply couldn't capture the true nature of radiation. Enter Max Planck, the quantum revolution's hero. By introducing the radical concept of energy quantization, Planck solved the ultraviolet catastrophe. His groundbreaking approach used Bose-Einstein statistics to model radiation. The key insight? Energy is not continuous, but comes in discrete packets. Each packet's energy depends on the radiation's frequency. This simple yet profound idea completely transformed our understanding of radiation. The mathematical formula we see isn't just equations, it's a window into the fundamental nature of energy itself. Planck's law describes the intensity of radiation emitted by a black body across different wavelengths. It avoids the ultraviolet catastrophe by showing that radiation intensity decreases at high frequencies, short wavelengths. At low frequencies, long wavelengths, the intensity increases, matching experimental observations. This law fundamentally changed our understanding of radiation and laid the groundwork for quantum mechanics. Let's delve deeper into how Bose-Einstein statistics explains black body radiation. Photons, being bosons, can occupy the same quantum state, a key feature that classical physics couldn't explain. At low temperatures, the radiation field behaves according to quantum statistical principles. The energy distribution of photons follows Planck's law, derived directly from applying Bose-Einstein statistics to quantum states. It's like revealing the secret choreography of light itself, showing how photons dance to quantum mechanical rules. Fermi-Dirac distribution applies to fermions, such as electrons and protons, which follow the Pauli exclusion principle. This principle states that no two fermions can occupy the same quantum state simultaneously. The Fermi-Dirac distribution gives the probability that a particle occupies an energy state at a given temperature. It's essential for understanding the behavior of particles in systems like metals and semiconductors, especially at low temperatures. Fermi-Dirac distribution applies to fermions, which follow the Pauli exclusion principle, preventing more than one particle from occupying the same quantum state. At absolute zero, all energy states up to the Fermi energy are filled, while those above are empty. As the temperature increases, some states above the Fermi energy become occupied, and some below may become vacant, reflecting the distribution's sensitivity to temperature changes. The free electron theory provides a microscopic understanding of electrical conductivity in metals by treating electrons as free particles moving among fixed positive ions, following quantum mechanical principles. Unlike classical models, these electrons follow quantum statistical rules, which are crucial for understanding conductivity and heat transfer. In the free electron model, electrons move within a crystalline lattice of positively charged ions, experiencing collisions that cause electrical resistance. The electron's energy levels are quantized within a continuous energy band, and they obey the Fermi-Dirac distribution, with a Fermi energy defining the highest occupied state at absolute zero. At higher temperatures, electrons gain thermal energy and can move to higher energy states. Electronic-specific heat is like measuring how much energy it takes to warm up the electron population in a material. At low temperatures, only electrons near the Fermi level can be thermally excited. Imagine a small group of dancers becoming more active while the rest remains still. The specific heat depends directly on the number of electrons near this critical energy level. As temperature increases, more electrons get excited, creating a linear relationship between specific heat and temperature. It's a beautiful demonstration of how quantum statistical principles govern even seemingly simple thermal properties. Fermi energy is the highest energy level occupied by an electron at absolute zero temperature. At non-zero temperatures, electrons can be thermally excited to higher energy levels, and the average energy of electrons depends on both temperature and electron distribution across these energy states. The Fermi energy can be calculated using the density of states and the total number of electrons. For a free electron gas in 3 dimensions, it is given by the formula: Fermi energy is proportional to the electron density raised to the power of 2/3. This slide explains how the average energy of an electron is derived from the Fermi-Dirac distribution at non-zero temperatures. At low temperatures, the average energy is roughly 3/5 of the Fermi energy. As the temperature increases and approaches the Fermi temperature, the electron distribution starts resembling the classical Maxwell-Boltzmann distribution, leading to more evenly distributed energy levels. Fermion behavior is crucial in understanding the degeneracy pressure that stabilizes compact objects like white dwarfs and neutron stars, remnants of dying stars. White dwarfs. White dwarfs are the remnants of stars that were not massive enough to become neutron stars or black holes. They are dense objects supported by electron degeneracy pressure. As white dwarfs contract, their Fermi energy increases, enhancing the degeneracy pressure. This electron degeneracy pressure arises because no two electrons can occupy the same quantum state, counteracting gravitational collapse. However, if the mass exceeds the Chandrasekhar limit of about 1.4 solar masses, this pressure cannot prevent further collapse. Neutron stars are more compact remnants formed from the collapse of massive stars. They are supported by neutron degeneracy pressure, similar to electron degeneracy pressure in white dwarfs, but involving neutrons. This pressure prevents further collapse due to Fermi-Dirac statistics, where neutrons obey the same principles as electrons. Neutron stars have extremely high densities and can have masses up to about 2 to 3 times that of the Sun, beyond which they may collapse into black holes. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.